Welcome to our final video in the moles unit. Today we're going to look at combustion analysis. So we've talked a lot about formulas and the fact that, we can't see them with a microscope, so we have to have ways to derive these different formulas, the ones that we've been looking at for most of the year. We saw how scientists, they get the percent by mass, they get the empirical formula, then they can get the molecular formula. So one of the most abundant types of compounds are what's called organic compounds. So an organic compound is one that is carbon-based, and they literally make up everything that's alive. So it's organic. The reason they use that word is because they originally thought that they were only found in living things. They're found in a lot more than living things, but everything that's living, the backbone of them is organic compounds. So organic compounds are ones that just have this carbon chain. So it's going to be a wide number of carbons bonded together, and this can go on to all kinds of numbers. The basic parts of any organic compound is just carbon and hydrogen. You can have other things mixed in there, but carbon and hydrogens are kind of the required ones. Other things you're going to find, oxygen's very common, nitrogen is, sulfur, phosphorus, other elements like that that can also fit within these carbon chains. But all of them have to have carbon and they have to have hydrogen. And that's what makes up an organic compound. They can be something as simple as methane, which is CH4, all the way up to glycine, which is an organic or an amino acid that we find in our body, which is C2H5NO2. What makes these so important is not only that they help us function with life, they make up pharmaceuticals. A lot of the foods that we eat have these organic compounds, flavorings, food colors, all made from organic things, but also there's such a wide variety of different compounds that can make up organic molecules. If we think of something like sodium and chlorine, how many different combinations of molecules is there that use sodium and chlorine? There's one, because sodium is positive when it reacts and chlorine's negative, and so the only thing that they can form is NaCl. There's no other combinations of sodium and chlorine, so it's simple. Scientists one time in the past, they figured out that sodium chlorine is NaCl, and that's it. We're done with it. Organic compounds, though, we're still finding new ones because there's all kinds of arrangements you can have. Just take any of these players right here, and there's an infinite number of possibilities of arrangements that we can use on these molecules, and then use them for different things. There's a whole branch of chemistry called natural chemistry, and what they do is they find things out in nature, and then they try and figure out, okay, what's the molecule that makes this plant, this animal do this? Here's a new poison that we found inside of this fish. Let's figure out what that molecule is. All of those poisons and stuff that they're going to be finding, they're going to be organic molecules. One of the ways that they can find organic molecules or figure out what the formula is to burn them. So if we think of a combustion reaction we learned is a hydrocarbon that's reacting with oxygen to produce carbon dioxide and water. And a hydrocarbon is just something that has a certain number of carbons, we'll say CX, there could be any number down there, and hydrogens, and any number down there as well. And then they can be attached to oxygen, nitrogen, sulfur. So really, it's an organic molecule. So an organic molecule is a type of hydrocarbon, which means it can burn, it can combust. So we can use this property, we can use balanced equations to figure out then, all right, if we know that they're going to make carbon dioxide and water, what is the identity of that hydrocarbon? We can do this through what's called combustion analysis that we're going to take a look at today. So the stoichiometry that goes into combustion analysis, it's a little bit tricky, but if you kind of follow these steps that I'm going to give you, do a little bit of practice, you can get this. So let's think of a combustion this way. We have this unknown organic molecule. We're going to combine it with oxygen, give it the sparks, light it on fire, burn it, and then we're going to collect the carbon dioxide and the water that's produced. So if we look at our reactants, remember, whatever we start with has to essentially add up to equal what we end with. So we see one of our products is carbon and another one is hydrogen. Well, where did that carbon and hydrogen come from? Because there's no carbon and hydrogen on this side. So they have to come from that unknown right there. That means if we figure out how much carbon dioxide we produce, that will tell us how much carbon was in the original molecule. So we can use the amount of carbon dioxide to tell us how much carbon there was. we can use the amount of hydrogen that's in the water to tell us how much hydrogen there was in our unknown, and use that to help us formulate then what the molecule is. So C what? H who? Also, in that molecule, there could be oxygen, there could be nitrogen, there could be phosphorus. We would see what the products are to help us figure that out. The tricky thing is, let's say that there is a certain amount of oxygen in that molecule. So the oxygen that's in the carbon dioxide and in the water, it's going to come from the unknown and from the oxygen that's in the reaction. So there's two sources of oxygen, both of our unknown and the oxygen gas that we put in to help this burn. So what we need to do then is we would figure out, okay, how much oxygen do we put in? And then subtract that from the oxygen over on this side, whatever's left over, that would be the oxygen from the unknown compound. Alright, so here's what the laboratory setup would look like. We would have these 3 chambers, and then oxygen would feed in through this end, and we would just keep pumping oxygen in there, so it's not going to be limiting reagent. Our limiting reagents would be the organic sample, and this organic sample has to be a known amount, so we would know how many grams we have in there. So we would mass that out, know how many grams there are, and we would combust it. So we would heat it up in there so it would burn, and then as it burns, it would flow through this little chamber right here, and it would go first to the H2O absorber and then to the carbon dioxide absorber. So this would be very, very similar to the principles we've already done in lab. Before this reaction begins, before we have started, we would get the mass of our H2O absorber, and we would get the mass of our CO2 absorber. So we would know initially how much they weigh. Then after we burn them, the mass of this one would increase, and the mass of that one would increase. So then knowing what the initial mass was, and we would subtract the final mass from the initial mass. So we would know how much it weighed to begin with. That would be our initial mass. We would know how much it weighed at the end. That would be our final mass. And we'd subtract those two. That would tell us, if we were looking at the H2O absorber, the grams of water that's absorbed. If we were to do it for the CO2 absorber, it would tell us the grams of CO2 that were absorbed, and therefore the amount of water that's produced and the amount of carbon dioxide that's produced. Once we know the amount of carbon dioxide that's produced, we would know the amount of carbon that was in our organic sample, and we would know the amount of hydrogen that's in our organic sample. And we can do some stoichiometry then to figure out the empirical formula. From the empirical formula, we can figure out the molecular formula. So a typical combustion analysis question or problem that you'll be given, they'll tell you the known amount of organic sample. So they'll say you had 1.7 grams of blah, blah, blah. They'll tell you the grams of water that was produced, and they'll tell you the grams of carbon dioxide that's produced. So you'll have 3 numbers that you will use to then figure out your empirical formula. They might also give you the molecular mass, which you would use to convert the empirical formula into the molecular formula. Alright, go ahead and stand up and stretch a little bit, maybe go to the bathroom, get yourself a bowl of ice cream, then come back, and let's try and tackle one of these combustion analysis problems. So this first problem, 2.04 grams of a sample containing C, H, and O. So that right there, that is our unknown organic molecule. Okay, so that's what's starting in the combustion chamber, and there's our known amount of it, so we have 2.04 grams of it, and it underwent a combustion analysis. We got the mass of the carbon dioxide catcher, and we found out that it increased by 4.49 grams. That means we have 4.49 grams of carbon dioxide, and the water chamber increased by 2.45 grams, so we had 2.45 grams of H2O. First thing we want to do, so step number 1, is to figure out how much carbon was in our original sample. So remember, all of the carbon that's in the original sample is going to be converted into carbon dioxide. So if we figure out how much carbon there is in the carbon dioxide we produced, that's going to tell us how much carbon there was in the initial sample. So this is where we're going to pull out a little bit of stoichiometry. So reach back in our memories, and we know we have 4.49 grams of CO2. And let's convert that over. So we'll have grams of CO2 on the bottom. Why grams of CO2 on the bottom? Because it's on top right there, and anything that's on top has to go onto the bottom. And we're going to convert that over to moles of carbon dioxide. So moles of CO2. And 1 mole of CO2 is 44.0 grams. And grams cancels out grams. Now we want to figure out how many carbons there were in the compound. So If we have 1 mole of CO2, 1 mole of CO2 has 1 carbon and 2 oxygens. So that means from 1 mole of carbon dioxide, we would have 1 mole of carbon. And to figure out how many grams of carbon there were in our initial sample, those will cancel each other out. 1 mole of carbon, because whatever's on top has to go on the bottom, is 12.0 grams of carbon. So plug that into our calculator, 4.49 times 12.0 divided by 44, and that tells us our initial sample had 1.22 grams of carbon in it. Okay, so we've just taken our amount of carbon dioxide and converted it into grams of carbon. Let's do the same thing with the water, and what do we use water to find? We use it to find our hydrogen. So let's figure out how many grams of hydrogen there were in our original sample. So we have 2.45 grams of H2O. 1 mole of H2O is 18.0 grams. That cancels out that. Now, 1 mole of H2O, we are looking for hydrogens. And how many moles of hydrogens is there in 1 mole of water? Well, it's H2O. That means there's 2 moles of hydrogen for every 1 mole of water. And 1 mole of hydrogen weighs in at 1 gram of hydrogen. So that means our initial sample had 0.27 grams of hydrogen in it. So it had 1.22 grams of carbon and 0.27 grams of hydrogen. It also contained oxygen, we can see in the question. So then how many grams of oxygen did it contain? Well, it had 1.22 grams of carbon, and it had 0.27 grams of hydrogen. So the hydrogen and the carbon made up 1.49 grams of the molecule. But the molecule weighed 2.4, our sample weighed 2.04 grams. So if 1.49 grams of it was carbon and hydrogen, what makes up the rest of it? Oxygen. So if we have a 2.04 gram sample and 1.49 grams of it was carbon and hydrogen, that means the oxygen weighed in at 0.55 grams. So there we go. We have the mass of oxygen, we have the mass of carbon, and we have the mass of hydrogen that make up our CHO unknown organic molecule. So let's use that information then, just like we would for an empirical formula question. So from here on out, it should be familiar territory. We have our grams right here, and we're just going to convert those into an empirical formula. So instead of having the percent of a molecule and then using that to figure out grams, we have our grams given to us right now. We're going to convert it to moles, divide by the smallest, and learn its empirical formula that way. So if we have 1.27 grams of carbon, 1 mole of carbon is 12.011. We're going to use some more significant figures. And that means we have 0.10 moles of carbon. And we could do the same thing with the other 2 atoms as well. And with that, we can see we have 0.27 moles of hydrogen and 0.034 moles of oxygen. Now we divide by the smallest number, which would be 0.034. And that's going to give us the ratio of all of the molecules to each other. And so for this one, we get 2.9, which is approximately 3. For this one, we get 7.9, which is approximately 8. And for our last one, obviously, we're going to get 1. So that means the empirical formula for this molecule is C3H8O. So there we go. We just figured out the identity of a mystery organic molecule by burning it, analyzing what it produces and how much it produces, and then doing some empirical formula calculations. Let's go ahead and practice this one more time. We'll actually go a little bit further this time because I've given you now the molar mass, and so this would be the actual molar mass of this compound. So once we figure out its empirical formula, we can also figure out its molecular formula. Not only that, but we've thrown nitrogen in here as well. So not only do you have to figure out how many moles of carbon there is, how many moles of oxygen there is, and how many moles of hydrogen, you also have to figure out how many moles of nitrogen. Now, thankfully, I've already told you how many grams of nitrogen we produce. This should be a pretty easy step. Just convert it into moles once you get to that part. So let's shrink this down. And this molecule is made up of 4 different elements then. So carbon, hydrogen, oxygen, and nitrogen. We're going to have to use the same process that we just learned about to get carbon, hydrogen, and oxygen. Nitrogen we're already given. The mass of nitrogen is right there. Okay, so at this point, if you feel comfortable or you think you want to give it a shot, pause the video, practice this one by yourself, see if you can get the empirical formula, the molecular formula. Once you get to the end or once you get stuck, go ahead and resume the video, follow along, check your answer or get some help, and hopefully you can start to get the hang of it. Alright, I'm going to move fairly quickly through this part because I'm assuming that we're fairly good with stoichiometry by now, so you don't need me to walk you through every step of that. So to find our grams of carbon, let's do carbon first, and we have 1.321 grams of CO2. Okay, so here's our stoichiometry setup. Grams of carbon dioxide, cancel out grams of carbon dioxide, moles, 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 and moles, and we're left in the end with grams of carbon. So if we solve that out, we would find out that the initial molecule had 0.3605 grams of carbon in it. Now we could do the same thing with hydrogen, and we get the hydrogen from our water, and we found that there was 0.325 grams of H2O. So our stoichiometry would look like that, and we can cancel out units. And we're left in the end with grams of hydrogen, and we find out that the initial molecule had 0.0364 grams of hydrogen in it. Now, finally, let's figure out how much oxygen there was inside of that molecule. Well, if we had 0.3605 grams of carbon, and we had 0.0364 grams of hydrogen, and then we also know that nitrogen weighs in a grand total of 0.0421 grams. So we can add that in there, 0.0421 grams of nitrogen. That equals 0.439 grams total. And so then we know that we had 0.487 grams of our quinine sample. Subtract from that the 0.439 that makes up the carbon, hydrogen, and nitrogen. And that tells us we have 0.0480 grams of oxygen in our molecule. So there we go. We now have the 4 pieces, the 0.3605 grams of carbon, 0.0364 grams of hydrogen, 0.0421 grams of nitrogen, and 0.0480 grams of oxygen. We can now convert those into moles, divide by the smallest, figure out our empirical formula. From there, figure out the molecular formula. So here's our 4 different pieces, and we're going to convert all of those into moles using some basic stoichiometry. From that, we can see we have 0.030 moles of carbon, 0.036 moles of hydrogen, 0.003 moles of nitrogen, 0.003 moles of oxygen. Let's divide by the smallest, which would be the 0.003. And get our ratio. And the ratio comes out as 10 to 12 to 1 to 1. So that means our empirical formula is going to be C10, H12, N, and O. So now we need to turn that into our molecular formula. So remember, this is just the ratio, so 10 to 12 to 1 to 1 is the ratio for this quinine molecule. Figure out what the molecular formula is, we need to figure out what the molecular mass is of this empirical formula. And the formula mass of it, if you add up all of its components, comes out to about 162 grams per mole. So now we need to do some division. If the molecule itself, the real one, weighs 324 grams per mole, got that from the question up there, and the empirical formula weighs 162, what factor does it change by? It changes by a factor of 2. So it means we need to take everything inside of here and multiply it by 2. That means the molecular formula is going to be C20H24 N2O2. And there you go. We just did a combustion analysis problem. We figured out what the molecular formula is for a mysterious compound called quinine. So basic procedure for analysis, combustion analysis. Use carbon dioxide to figure out how many grams of carbon. Use water to figure out how many grams of hydrogen. And then use the total mass of the molecule subtracted from the mass of the knowns to figure out your mass of oxygen. Once you have those, and nitrogen if it's thrown in, or sulfur, or any of the other molecules, you can figure out how many moles, divide by the smallest, get the empirical formula, and if need be, get the molecular formula. That's it. Review this a little bit. We'll practice in class next time I see you guys, and you'll get the hang of it, I promise.